There is a planet hanging in the darkness just beyond the reach of your outstretched hand, a world so beautiful, so impossibly symmetrical, that the first human being to point a telescope at it thought his instrument must be broken. He thought he was seeing things. He thought the universe was playing a trick on him. And in a way, it was. Because that planet, that ringed, golden, gaseous giant drifting silently through the cold outer reaches of our solar system, has been hiding a secret for as long as human beings have been alive to wonder at it. A secret so fundamental, so quietly revolutionary, that unlocking it required the most powerful space telescope ever constructed by human hands. And even then, even with all of that technology, all of that precision, all of those years of patient waiting and careful observation, the answer still arrived as something of a surprise. Let that thought settle gently in your mind as you breathe. Because tonight, we are going to travel together to Saturn. We are going to drift past the outer planets, past the cold and the silence, past the place where sunlight grows faint and the stars begin to feel very, very close. We are going to look at those rings, those famous, breathtaking, luminous rings, and we are going to ask the question that astronomers have been wrestling with for decades. A question so deceptively simple that it almost sounds foolish to ask, and yet so profoundly difficult to answer that it occupied some of the greatest scientific minds of the 20th and 21st centuries. How old are Saturn's rings? That is the question. Quiet and small in its phrasing, enormous in its implications. Because the rings of Saturn look ancient. They look like something that has always been there, something as permanent as the planet itself, something woven into the fabric of the solar system from the very beginning. When you see those rings in a photograph, those broad, sweeping arcs of ice and rock and dust, catching the distant sunlight and throwing it back at you in ribbons of pale gold, your instinct, your deep human instinct, is to assume they are primordial. To assume they have always existed. To assume that Saturn without its rings would be like a question without an answer, incomplete, diminished, wrong somehow. And for most of human history, that assumption went completely unchallenged. For most of human history, no one even thought to question it. Saturn had rings. The rings were part of Saturn. And that was simply how it had always been, and how it would always be, until it wasn't. Because in the final years of the 20th century, and then with gathering urgency in the early years of the 21st, a quiet revolution began to stir in planetary science. Astronomers started looking more carefully at the rings, not just admiring them, not just cataloguing them, but measuring them, probing them, asking hard and uncomfortable questions about what they were made of and how much they weighed and how they interacted with the space around them. And what they found, what they slowly, carefully, painstakingly found, was troubling. The data did not tell the story everyone had expected. The data told a different story entirely. A story in which Saturn's rings, those ancient, permanent, primordial rings, might not be ancient at all. Might not even be old by the generous standards of cosmic time. Might, in fact, be shockingly, almost embarrassingly young. A fleeting feature of a much older world. A temporary accessory on a planet that was already billions of years old when they arrived. Imagine that for a moment. Imagine that the most recognizable feature of the most recognizable planet in our solar system might be younger than the dinosaurs. Might have appeared in the sky while life on Earth was already ancient and complex and crawling toward consciousness. That is the possibility that began to haunt planetary science. And for decades, there was no way to know for certain. There was evidence pointing one direction. There was evidence pointing another. There were brilliant scientists on both sides of the argument, each marshalling data and models and careful reasoning, and the question simply hung there. Unresolved. Patient. waiting until the James Webb Space Telescope arrived and pointed its golden mirror at Saturn and began to see. Breathe in slowly and let your body relax a little more deeply into wherever you rest. Because we are in no hurry tonight. The universe has waited billions of years to reveal this secret. It can wait a little longer while we find our way there together, gently and unhurriedly, through everything we need to understand before the answer finally comes. So let us begin, as all good journeys do, at the beginning. Let us go back to Saturn itself. Let us remember what this world is, what it feels like to contemplate it, and why it has held human imagination in its quiet, golden grip for so very, very long. Saturn is the sixth planet from the Sun, orbiting our star at a distance so vast that it is almost impossible to hold in the mind all at once. It circles the Sun at an average distance of roughly 9.5 astronomical units, 9.5 times the distance from the Earth to the Sun, which means that a beam of light, traveling at the inconceivable speed of nearly 300,000 kilometers every single second, still takes more than an hour and 20 minutes to make the journey from the Sun to Saturn's cloud tops. The planet drifts in a realm where sunlight arrives pale and attenuated, about 100 times dimmer than what we experience here on Earth, and where the temperature in the upper atmosphere plunges to around -178 degrees Celsius. It is cold out there, and dark, and very far from anything we might recognize as home. And yet the planet itself is enormous. Saturn is the second largest planet in our solar system, surpassed only by Jupiter, and its scale is something that resists easy comprehension. The planet's diameter at its equator is roughly 116,000 kilometers, about 9.33 times the diameter of Earth. If the Earth were a grape, Saturn would be a beach ball. If you could hollow out Saturn and fill it with Earths, you could fit more than 700 of them inside. The planet's mass is 95 times the mass of our own world, and yet despite that tremendous mass, Saturn is paradoxically the least dense planet in the solar system, less dense, in fact, than liquid water. If you could find an ocean large enough to hold it, Saturn would float. That strange, almost dreamlike fact is a consequence of its composition. Saturn is made primarily of hydrogen and helium, compressed and layered and heated in ways that produce no solid surface whatsoever, just a gradual, vertiginous deepening from gas to liquid to something stranger still at the planet's core. Saturn rotates extraordinarily quickly for such a large body, completing one rotation in just over 10.5 Earth hours, and this rapid spin has flattened the planet at its poles and stretched it at its equator, giving it a subtly oblate shape that becomes apparent when you look at it carefully. The planet's axis is tilted at about 27 degrees, slightly more than Earth's own axial tilt, and this tilt means that Saturn experiences seasons, long, slow seasons that last more than 7 Earth years apiece, given that Saturn takes nearly 29.5 Earth years to complete a single orbit around the Sun. These are the basic facts of Saturn, the measurements and numbers that describe it from the outside. And they are extraordinary in their own right. But they are not why Saturn has captivated human beings for so long. The numbers are not what makes a person catch their breath when they first see Saturn through even a modest backyard telescope on a clear and quiet night. What does that, what has always done that, since the very first time a human eye was pressed to a lens and aimed at that pale yellow point of light, are the rings. The first person to notice that something was unusual about Saturn through a telescope was Galileo Galilei, in the summer of 1610. Galileo had just made his telescope, a revolutionary instrument for its time though almost comically primitive by modern standards, and he was methodically turning it toward the planets, recording what he saw. When he looked at Saturn, he saw what appeared to be two smaller spheres, one on either side of the main planet, touching it almost like a pair of ears, or perhaps like companion bodies locked in an impossibly close orbit. He wrote in his notes that Saturn appeared to be triple, a central body flanked by two smaller ones. He was puzzled. He was intrigued. And then, in 1612, he looked again and the flanking bodies had vanished. Saturn appeared perfectly, frustratingly round. He was baffled, and a little unsettled, and he wrote with an undercurrent of something like unease that he didn't know what to make of it, as if the planet had swallowed its companions. What Galileo was seeing, of course, was the ring system viewed at different angles as both his telescope and Saturn moved through space. When the rings were edge-on to Earth, they nearly disappeared. When they were tilted, they appeared as those mysterious flanking protrusions. But Galileo's telescope was not good enough to resolve what was actually there, and the true nature of the rings, flat, circular, composed of countless separate particles, orbiting the planet in a disk, was not understood until the Dutch astronomer Christian Huygens proposed the ring hypothesis in 1659, using a much better telescope and careful reasoning to arrive at a picture that was essentially correct. Since then, Saturn's rings have been one of the most studied, most photographed, most beloved features of the entire solar system. Every telescope that has been pointed at them has revealed new detail, new complexity, new layers of structure that were invisible before. And as we have come to understand that structure more deeply, the mystery of the rings has not diminished, it has grown. The ring system of Saturn is breathtaking in its complexity when you begin to explore it up close. From Earth, the rings appear as a broad, relatively simple disk of light surrounding the planet, divided into obvious bright and dark bands when you look carefully enough. But when you send a spacecraft there, when you get close enough to really look, what you find is something of almost incomprehensible intricacy. Thousands of individual ringlets, each one a river of orbiting particles following its own slightly distinct path around the planet. Gaps and edges sculpted by the gravitational influence of Saturn's many moons. Waves and spirals and braided structures that look almost organic, almost alive in their complexity. The main ring system, the broad disk visible even in small telescopes, is commonly divided into several named regions, each with distinct properties. Moving outward from the planet, you first encounter the faint and tenuous D ring, barely visible even to modern instruments, pressing closest to Saturn's cloud tops. Beyond that lies the C ring, also called the creep ring for its relative translucency and grayish color, a broad and somewhat diffuse band of particles stretching across tens of thousands of kilometers. The C ring is real and measurable, but it allows starlight to pass through it, which tells astronomers something important about how thinly spread its material is. Beyond the C ring comes the B ring, the brightest and most massive of the main rings, the one that catches your eye first in any photograph of Saturn, the one that blazes with reflected sunlight and seems almost to glow from within. The B ring is dense and opaque, and for all its brightness, it guards its secrets well. Its mass, its exact composition, its precise relationship to the other rings, has been the subject of debate and careful measurement for decades. And then beyond the B ring, separated from the next region by a distinct and beautiful gap, we reach what may be the most famous empty space in the solar system. The Cassini division is a gap approximately 4,800 kilometers wide, wider than the continental United States is from east to west, that separates the bright B ring from the A ring beyond it. To the naked eye through a telescope, the Cassini division looks like a dark, empty space, a pause in the rings, a moment of silence between two acts. And for a long time, astronomers assumed it truly was empty, that the gravitational influence of Saturn's moons had swept it clean of particles. The truth, revealed by closer examination, is more nuanced. The Cassini division is not truly empty, but contains a relatively sparse population of particles, reddish in color and different in composition from the brilliant ice of the main rings. It is thinned, not erased, sculpted by resonances with the moon mimas into a clearing that is real and dramatic but not absolute. Beyond the Cassini division, the A ring stretches outward, slightly less bright than the B ring, slightly less massive, but still substantial and gorgeous, containing within it a smaller gap called the Encke gap where the tiny moon Pan orbits, and the Keeler gap maintained by another small moon called Daphnis, whose passage through the ring material creates sinuous, wave-like edges along the gap's boundary that are almost impossibly beautiful when captured in close-up images. And beyond the A ring, there are further, fainter structures, the narrow F ring just outside, kept in place by shepherd moons, and the diffuse G and E ring still further out, each one thinner and more ghostly than the last, until the ring system dissolves into the emptiness of interplanetary space. All of this glorious, complex, billion-kilometer spanning structure is made of extraordinarily simple stuff when you get down to it. The rings of Saturn are composed overwhelmingly of water ice. Not rock, not metal, not exotic high-temperature minerals, but water ice, the same substance that forms snowflakes on Earth, the same substance that made up much of the raw material of the early solar system. Individual particles in the rings range from tiny grains barely the size of a sand grain to boulders several meters across, and they are mostly, brilliantly, astonishingly white. The brightness of Saturn's rings, the reason they gleam so vividly in reflected sunlight, is a direct consequence of this icy composition. Ice is reflective. Ice catches light and throws it back. And the rings of Saturn are, or at least the main rings are, nearly as reflective as fresh-fallen snow. I say mostly, because there is contamination. There is a thin layer of dust, of dark carbonaceous material, of reddish organic compounds, mixed in with the ice. This contamination is important. It is one of the keys to the age debate. Because contamination accumulates over time. The dark material arrives from outside the ring system, from meteoroid impacts, from the general drift of cosmic dust that permeates our solar system, and once it arrives, it stays. It coats the ice particles, darkens them gradually, shifts their reflectivity downward in a slow and steady process. And the rate at which this happens, the rate at which the rings should be accumulating this dark material from the environment around them, is something astronomers can measure. Or at least estimate. And when you try to work backward from how contaminated the rings currently are, when you ask how long it would take to accumulate this much dark material at this rate of delivery, you get a number. A number that, when it first emerged from careful analysis of Cassini spacecraft data, shocked the scientific community. But we are getting ahead of ourselves. Let the idea settle. Let it drift in the back of your mind, quiet and patient, like a question written on the surface of a pond. How long does it take to make rings that look like these? The debate about the age of Saturn's rings did not begin suddenly, and it did not arrive with a single dramatic announcement. It grew, the way most scientific controversies grow, slowly, incrementally, as better data began to complicate a picture that had seemed simple. For most of the 20th century, the prevailing assumption among astronomers was that Saturn's rings were ancient, as old as the solar system itself, perhaps 4.5 billion years old, relics of the same primordial cloud of gas and dust that collapsed to form the Sun and all the planets around it. This view felt natural, felt right, felt consistent with the general picture of a solar system that formed all at once and has been quietly aging ever since. The rings looked permanent. The rings looked primordial. The rings looked like they belonged to a place where time operated differently, on scales so long as to make words like old and young nearly meaningless. The ancient rings hypothesis rested on several lines of reasoning, each one internally consistent and seemingly compelling. The first was simply the enormous scale and mass of the ring system itself. The main rings of Saturn contain an enormous amount of material. The precise figure was long uncertain, but estimates suggested something on the order of the mass of a small moon, perhaps comparable to the mass of Saturn's moon Mimas, compressed into a disk. Creating something this massive, this vast, this elaborate, from scratch at a late stage of solar system history would require an enormous triggering event, the destruction of a large moon or the catastrophic disruption of a major cometary body. Such events, the ancient rings camp argued, were far more likely in the chaotic early solar system, when the planets were still forming, when debris was abundant, when the gravitational environment was violent and turbulent and full of collisions. The early solar system was a demolition derby. The later solar system, by comparison, is quiet. Creating rings today, or even a few 100 million years ago, would require a much rarer and more extraordinary event. The second argument for ancient rings was more structural. Saturn's ring system is extraordinarily complex. It has had time to develop all of that intricate fine structure, those thousands of ringlets, those resonance gaps, those sculpted edges. Could all of that complexity have developed in just a few 100 million years? Some modelers argued no, that the layered, elaborate structure of the ring spoke of deep time, of billions of years of slow orbital evolution, of gravitational shepherding by moons, of gradual self-organization into the patterns we see today. The rings felt, in other words, like something ancient precisely because they were so thoroughly settled, so finely ordered, so exquisitely detailed. And there was a third, more philosophical argument, one that carries less scientific weight but is worth acknowledging because it influenced thinking for a long time. We live on a planet that orbits the same sun as Saturn. Our solar system formed at one moment, some 4.5 billion years ago. The planets and moons that exist today are, with some exceptions and variations, the planets and moons that have existed since the beginning. There is something deeply satisfying, something deeply consistent with our picture of a stable and long-evolved solar system, about the idea that Saturn's rings have always been there, that they are not a recent development, not an accident of the particular moment in cosmic history when we happen to exist, but a permanent and ancient feature of our planetary neighborhood. The alternative, the idea that we are somehow lucky enough to be alive at the brief moment when Saturn happens to have rings, carries with it an uncomfortable whiff of the cosmically improbable. Astronomers have a word for this kind of discomfort. They call it the Copernican principle, the idea, first articulated by Nicolaus Copernicus and later elevated into a broad philosophical stance, that we should be wary of assuming our particular vantage point in space or time is special. If Saturn's rings are young, if they formed only a few 100 million years ago and will dissolve back into the planet within another 100 million years or so, then we happen to be observing Saturn during the very brief window when it has rings at all, out of a total lifespan of 4.5 billion years. The odds of that seem low. Uncomfortably low. Suspiciously low. And scientists are, rightly, suspicious of conclusions that require the universe to have arranged things conveniently for our benefit. But the data did not care about anyone's comfort or their philosophical preferences. And the data, slowly and insistently, began to point in a direction that the ancient rings camp did not want to follow. The first serious challenge to the ancient rings hypothesis came from thinking carefully about contamination, that gradual darkening of the ring particles by infalling dust and organic material. The rings of Saturn are brilliantly white. They are, as mentioned, nearly as reflective as fresh snow. But fresh snow does not stay white forever. It accumulates dust and soot, and tiny particles of everything that drifts through the air, and over time it becomes gray and dirty and finally indistinguishable from the ground beneath it. The same process operates in the rings. Meteoroids continuously bombard Saturn's ring system, each tiny impact vaporizing a small amount of ring material and mixing in a small quantity of dark, carbon-rich material from the impacting body. The dust of interplanetary space, dark and ancient and organically stained, also settles gradually onto the ring particles. The process is slow, but it is steady, and it is irreversible. Now, planetary scientists had worked out, with reasonable confidence, the rate at which this contamination process operates around Saturn. The flux of micrometeorite impacts, the density of interplanetary dust in the outer solar system, these things are measurable and constrained. And when you apply those rates to the current brightness of Saturn's rings, when you ask how long it would take to start with clean, pure water ice and end up with rings exactly as bright as the ones we observe today, you get a number that is shockingly, provocatively small. Not for billion years. Not even 1 billion years. The contamination argument pointed to something on the order of a few 100 million years at most. Perhaps much less, perhaps as recently as 10 million years ago. This was the young rings hypothesis, and it arrived not as a wild speculation but as a sober, data-driven inference from the physics of contamination and reflectivity. If the rings were 4 billion years old, they should be much darker than they are. The fact that they are still so brilliantly white suggests they are relatively fresh, that they were made from clean ice relatively recently and have not yet had time to accumulate the full coating of dark material that billions of years of bombardment would inevitably produce. The young rings camp, led by researchers including Luke Duntz and later Jeff Cousy and R. Clark, among others, began building a case that was simultaneously elegant and alarming in its implications. They argued that the brilliant whiteness of the rings was not just an aesthetic feature but a chronological clue, a kind of cosmic timestamp written in the language of reflectivity and contamination rates. Clean ice means young ice. And young ice means the rings must have formed much more recently than anyone had assumed. The ancient rings camp did not concede easily, and they were right not to. Because the contamination argument, compelling as it was, rested on assumptions that could be challenged. The rate of micrometeorite bombardment around Saturn in the distant past may have been different from the rate today. The early solar system was much more violent, and if that violence had contributed disproportionately to contaminating the rings in the ancient past, the modern rate might underestimate the historical rate, and the rings might be older than the current brightness alone would suggest. Furthermore, there are processes that can refresh the rings, that can clean them over time, and meteoroid impacts that excavate fresh, clean ice from the interiors of ring particles, exposing new surfaces that have not been contaminated. Resurfacing mechanisms could, at least in principle, make ancient rings look younger than they are by continuously recycling the surface material and exposing pristine ice from beneath. These were genuine counterarguments, and they kept the debate alive for decades. The ancient ring scientists and the young ring scientists each had their ammunition, and neither side could land the decisive blow that would end the argument, because neither side had access to the one measurement that would settle the question most directly. That measurement was the mass of Saturn's rings. Mass matters because it is tied to both the age question and the contamination question in a crucial way. Here is the reasoning. If the ring started out as a certain amount of pure ice, a specific quantity of clean, frozen water, and have been accumulating dark material ever since, then the total mass of the rings today is the original mass of ice plus the accumulated mass of contaminants. If you know the current mass of the rings, and you know how much dark material is present in them now, and you know the rate at which that dark material has been arriving, you can work backward to constrain both the original mass and the age. A very massive ring system that is relatively lightly contaminated could be either ancient and massive or young and moderate. The two variables are entangled. But if you can pin down the mass precisely, the entanglement can be unraveled. For decades, the mass of Saturn's rings was one of the most important unknown quantities in planetary science. Estimates existed, but they were indirect, based on how the rings gravitationally perturbed the trajectories of spacecraft that flew past them, or on models of how ring particles interact with each other, or on measurements of ring brightness combined with assumptions about particle size and composition. None of these methods was precise enough to settle the debate. The error bars were enormous. You could fit ancient rings and young rings both comfortably within the range of plausible values. What was needed was a direct measurement. A spacecraft that could fly close enough to the rings, close enough to actually feel the gravitational tug of the ring material itself, and measure that tug with sufficient precision to determine the true mass. A spacecraft that could, in effect, be weighed down by the ring's own gravity as it passed between them and the planet, and use the precise degree of that gravitational influence to calculate how much material was actually there. No spacecraft had ever done that. For all the decades of Saturn observation, for all the flybys and orbital surveys and remote sensing campaigns, no mission had ever ventured into the narrow gap between Saturn's innermost rings and the planet's upper atmosphere. It was a region of space that was considered too dangerous, too risky, too uncertain to attempt, until Cassini. And it is to Cassini that we will turn next, with its long and patient vigil above the rings, its final dramatic dive between ring and planet, and the gift of data it left behind, a gift that brought us closer than ever before to answering the question, but still, in the end, not quite close enough. Because the mystery of the rings, like all the best mysteries, was not going to yield easily. It was going to require one more instrument, one more set of eyes, one more act of extraordinary technological ingenuity before it finally, gently, surrendered its secret. But let that thought drift for a moment before we follow it forward. Let yourself settle more deeply into your breath, more deeply into the quiet of wherever you are resting tonight. Outside, if the sky is clear and if you know where to look, Saturn is out there somewhere, drifting slowly through its great elliptical orbit, surrounded by those brilliant rings, carrying its secret through the cold and the dark. And the light reflecting from those rings, the light that tells us they are young, or old, or something in between, has been traveling toward us for more than an hour and 20 minutes, crossing the void at 300,000 kilometers per second, carrying all of this history, all of this mystery, all of this quiet astronomical drama embedded in its spectrum. That light arrives at your eyes as a pale gold point in the darkness, unremarkable to the casual glance, extraordinary to anyone who knows what they are looking at. A planet with a secret. A secret that took humanity for centuries of looking, and for centuries of improving our instruments and our understanding, to even begin to ask the right questions about. And the asking of right questions, in science as in life, is often more than half the work. The Great Age debate is not just a story about rings. It is a story about how science works, how certainty gives way to doubt, how comfortable assumptions meet uncomfortable data, how the most permanent seeming things in the universe sometimes turn out to be the most temporary. It is a story about the courage it takes to follow evidence where it leads, even when it leads somewhere disorienting, even when it tells you that what you thought you knew was incomplete, or wrong, or simply not yet understood deeply enough to be called knowledge at all. Saturn has been orbiting the Sun for 4.5 billion years. The question of whether its rings are as old as the planet itself, or whether they arrived a geological eye blink ago in cosmic terms, is not merely a technical question about mass measurements and contamination rates. It is a question about identity, about whether those rings are an essential, permanent part of Saturn, or a temporary garment draped over an older and more fundamental self. It is a question that touches, in its quiet way, on something almost philosophical about the nature of change and permanence in a universe that is always, always in motion. And the answer is coming. We are building toward it, step by patient step, the way the universe builds toward all its revelations, slowly, through accumulation, through the gradual layering of evidence upon evidence, observation upon observation, question upon question, until finally the picture resolves and something that was hidden becomes, at last, visible. Let that sense of slow revelation be your companion as you rest. There is no rush. The rings of Saturn have been waiting for us to find the answer. They can wait a little longer still. And you, wherever you are, in whatever quiet corner of the world you have made your resting place tonight, can let your body grow heavier and your thoughts grow softer and your breath slow to the rhythm of something patient and vast and utterly unhurried. Because the universe is telling us a story. And every good story deserves to be heard all the way to the end. And so we arrive at the moment of farewell. There is something quietly heartbreaking about the end of a mission that has given so much. When the Cassini spacecraft was launched from Cape Canaveral on the 15th of October, 1997, no one alive could have fully imagined what it would return to us over the decades that followed. It was a machine, yes, a carefully engineered collection of instruments and circuits and propulsion systems, but it became, in the minds of the scientists who guided it and the public who followed it, something closer to a companion. A traveler sent out into the dark on our behalf, recording everything it encountered with tireless, faithful precision. Cassini reached Saturn in the summer of 2004, after a journey of nearly 7 years and more than 3 billion kilometers. And from the moment it settled into orbit around the ringed planet, it began sending back wonders. It showed us storms that dwarfed entire continents on Earth. It revealed the hexagonal polar vortex at Saturn's North Pole, a geometric weather pattern so improbable it seemed almost designed, a six-sided hurricane larger than 2 Earths placed side by side, spinning with eerie mathematical precision in the cold Saturnian atmosphere. It discovered geysers of water ice erupting from the south pole of Enceladus, Saturn's small icy moon, suggesting a liquid ocean beneath the surface, an ocean that might, just possibly, harbor the conditions for life. But it is what Cassini told us about the rings themselves that matters most to our story tonight. And to understand Cassini's final gift, we must first understand the circumstances that made it possible. By the year 2017, Cassini had been orbiting Saturn for 13 years. Its fuel supply was running low, and the mission planners at NASA's Jet Propulsion Laboratory faced a decision that carried both scientific and ethical weight. The spacecraft could not simply be left adrift indefinitely. There was a real concern that if Cassini were to collide with Enceladus or Titan, Saturn's largest moon, it might contaminate those potentially life-bearing worlds with microbial stowaways from Earth. And so the decision was made to end the mission deliberately, precisely, and with purpose. Cassini would be guided into Saturn's atmosphere, where it would burn up like a meteor, its data transmitting until the very last moment. But before that final plunge, mission scientists designed something remarkable. They called it the grand finale. In the months leading up to Cassini's end, the spacecraft was maneuvered into a series of orbits that took it somewhere no probe had ever gone before, through the narrow gap between Saturn's innermost rings and the top of the planet's atmosphere. This gap, only about 2,000 kilometers wide, had never been explored directly. And in those final 22 orbits, Cassini gathered data of extraordinary scientific value. Imagine, if you will, the scene in Mission Control at the Jet Propulsion Laboratory during those final months. The scientists and engineers watching their screens, knowing that each transmission from Cassini might be one of the last. Knowing that every measurement taken in that narrow, unexplored corridor between rings and planet was irreplaceable. There is a particular quality to attention paid to things that cannot be repeated, a sharpness, a tenderness, and the team guiding Cassini through its grand finale must have felt both of those things in equal measure. What Cassini found in that gap was, in the most literal sense, illuminating. One of the most critical measurements it made was of the gravitational field of the ring system. By tracking subtle changes in Cassini's trajectory as it passed through the ring plane, scientists could calculate with unprecedented precision how much mass the rings actually contained. And the answer, when it came, was both surprising and deeply significant. The rings of Saturn, for all their visual magnificence, are surprisingly lightweight. The total mass of the ring system, all those billions of particles of ice and rock, stretching across hundreds of thousands of kilometers, amounts to roughly 40% of the mass of Enceladus, Saturn's small icy moon. To put that in terms that might help you feel it more viscerally, if you were to gather every single particle in Saturn's ring system and compress them together into a single body, you would end up with something roughly 100 kilometers across. A world the size of a small city. For rings that span a distance greater than that between the Earth and the Moon, that is a vanishingly small amount of material. And it was this measurement, this careful weighing of the rings by tracking the whisper of their gravity on a passing spacecraft, that gave the young rings hypothesis its most compelling evidence yet. Because mass matters enormously when you are trying to calculate age. The rings are constantly being contaminated by micrometeorites, tiny particles of dust and rock that drift in from beyond the solar system and gradually darken the ice. Scientists can estimate the rate at which this contamination accumulates. And if you know the current mass and purity of the rings, and you know how fast they are being dirted, you can work backwards to figure out how long they must have been there. The calculation, performed using Cassini's precise mass measurements, yielded a number that shocked many in the planetary science community. The rings, it seemed, could be no older than perhaps 400 million years. Some estimates pushed that figure even lower, as young as 10 million years. On the geological timescale of a solar system that formed 4.5 billion years ago, these are not ancient rings at all. They are newcomers. They are, by cosmic standards, practically brand new. But here is where the story grows more complicated and more beautiful. Because even Cassini's extraordinary measurements could not close the debate entirely. The grand finale data was groundbreaking, yes. It gave us the most precise ring mass measurement in history. It confirmed that the rings were being eroded by ring rain, a process by which charged water particles from the rings drift along Saturn's magnetic field lines and fall into the planet's upper atmosphere, gradually depleting the ring material over time. Scientists estimated that at current erosion rates, the rings could disappear entirely within 100 million years or so, a cosmically brief window that made their existence in our current era feel almost like an extraordinary coincidence. And yet, the ancient rings camp did not simply capitulate. They raised objections that were, in their own way, equally compelling. The mass measurement, they argued, might not tell the whole story. Perhaps the rings began much more massive than they are today and have been steadily losing material since their formation billions of years ago. Perhaps the contamination rates we observe now are not representative of contamination rates across geological time. Perhaps there were periods of greater bombardment, periods of relative quiet, variations that would make a simple linear calculation of ring age unreliable. Perhaps what we see today is not the original ring system at all, but a ring system that has been repeatedly refreshed and replenished by ongoing collisions and debris. There were even more subtle arguments. Some researchers pointed to the ring's extraordinary purity as evidence against youth. If the rings had formed recently, from the shattering of a moon or the capture of a comet, as the young rings hypothesis required, then they would have formed from a body that itself contained significant quantities of rock and silicate material mixed in with the ice. A freshly shattered moon would not produce rings of almost pure water ice. And yet that is almost exactly what the rings appear to be, at least in their innermost, brightest regions. For some scientists, that purity was not evidence of youth, it was evidence of a long, slow process of sorting and distillation that could only happen over billions of years. So there you have it. Cassini gave us the most precise measurements of Saturn's rings ever obtained. It weighed the rings, measured their composition, tracked their erosion, and dove through their shadow with instruments recording everything to the last possible moment. And still, the question of their age remained genuinely, stubbornly, beautifully open. On the 15th of September, 2017, at 6:16 in the morning Pacific time, Cassini entered Saturn's atmosphere at a speed of over 100,000 kilometers per hour and was destroyed. Its final signal, a pulse of radio waves that had traveled 1.5 billion kilometers across empty space, was received by the Deep Space Network antenna in Canberra, Australia, and then there was silence. A silence that felt, to those who had spent decades of their lives with this spacecraft, like the end of something irreplaceable. But science does not mourn for long, because science is always already looking forward. And even as Cassini was falling, even as the last of its transmissions were being recorded and archived, another instrument was being prepared, an instrument so powerful and so unprecedented that it would eventually take up where Cassini had left off and push the question of Saturn's age into territory that no telescope had ever reached. The James Webb Space Telescope. Let that name settle for a moment, the way names of great things are meant to settle, slowly, with appropriate weight. JWST is not simply a larger or better version of the Hubble Space Telescope, though it is certainly both of those things. It represents a genuinely different kind of seeing. To understand why JWST was able to tell us things about Saturn that no previous telescope could, we need to spend a little time understanding what makes it so fundamentally, so categorically different from what came before. Light, as you may have drifted past in earlier parts of our journey tonight, exists across a vast spectrum. What we call visible light, the colors that our eyes can detect, the warm oranges and cool blues and deep reds of a sunset, is only a narrow slice of that spectrum. Beyond the red end of visible light lies infrared radiation, sometimes called heat radiation, because every object in the universe emits it in proportion to its temperature. Warm things glow in infrared. And crucially, different molecules and chemical compounds emit and absorb infrared light at very specific, characteristic wavelengths, a kind of chemical fingerprint that can be read, if you have the right instruments, across billions of kilometers of empty space. The Hubble Space Telescope was primarily designed to observe invisible light and ultraviolet wavelengths. It gave us images of breathtaking clarity, images that changed the way humanity thought about the cosmos. But Hubble was largely blind to much of the infrared spectrum. The Spitzer Space Telescope, launched in 2003, was designed for infrared observation and returned extraordinary data about the cool universe, dusty star-forming regions, the heat signatures of distant galaxies. But Spitzer was a relatively modest instrument, limited in what it could resolve at the distances and scales needed to study planetary ring systems in chemical detail. JWST is different in almost every way that matters. Its primary mirror is 6.5 meters in diameter, roughly 2.5 times the diameter of Hubble's mirror, and it is composed of 18 hexagonal gold-coated beryllium segments that unfold in space like a flower opening in slow motion. But more than its size, it is its location and its sensitivity that set it apart. JWST orbits at a point called the second Lagrange point, or L2, approximately 1.5 million kilometers from Earth in the direction away from the Sun. At this distance, JWST can maintain an extraordinarily stable cold temperature, because to observe the faint heat glow of distant objects in the infrared, the telescope itself must be kept colder than anything it is trying to detect. It is kept below -230 degrees Celsius, shielded from the sun by a 5-layer sunshield roughly the size of a tennis court. This extraordinary cold, combined with the telescope's enormous mirror and its suite of highly sensitive instruments, gives JWST a capability that was simply impossible before its launch in December of 2021. It can detect the chemical fingerprints of molecules in planetary atmospheres, in ring systems, in the disks of gas and dust around newly forming stars, with a precision and sensitivity that leaves all previous telescopes behind. The two instruments most relevant to the Saturn observations we are building toward tonight are NIRCam and MIRI, the near-infrared camera and the mid-infrared instrument. NIRCam observes light in the near-infrared range, wavelengths of roughly 1 to 5 microns, where astronomers can detect the spectral signatures of water, ice, methane, and certain hydrocarbons with remarkable clarity. MIRI extends the telescope's reach into the mid-infrared, from roughly 5 to 28 microns, a region of the spectrum where thermal emission becomes detectable and where the chemical fingerprints of silicate materials and complex organic compounds are most clearly revealed. Think of it this way. If Cassini was a geologist standing on the surface of Saturn's ring system with rock hammers and chemical sensors, measuring the mass and composition of what lay directly beneath it, then JWST is an artist standing far away, perceiving the entire composition in a single glance, not by touching but by reading the light, interpreting the glow of wavelengths invisible to our unaided eyes, finding in those subtle gradations of heat and chemistry a story written in light itself. When astronomers first turned JWST towards Saturn in the summer of 2023, they did so with a set of carefully considered scientific goals. They wanted to examine Saturn's atmosphere in the mid-infrared in greater detail than had ever been possible from Earth orbit. They wanted to look at the rings and attempt to characterize their thermal emission, the faint glow of heat radiating from the ring particles themselves, and compare those thermal signatures against models of ring composition and age. And they wanted, perhaps most ambitiously, to look for the chemical signatures that might distinguish between a ring system made from recently shattered moon material and one that had been gradually accumulated and modified over billions of years. There was considerable anticipation in the planetary science community. Researchers who had spent their careers arguing for young rings and those who had argued for ancient ones both understood that JWST represented something qualitatively new, not simply better data of the kind they already had, but a different kind of data entirely. Infrared spectroscopy from a telescope of this sensitivity had the potential to reveal things about ring composition and thermal behavior that no amount of radio tracking or visible light photography could show. And then, the images began to arrive. The first thing that struck the scientific team, and it struck them with a force that required careful reflection before anyone was quite sure what they were seeing, was the darkness. Saturn, in JWST's mid-infrared imaging, appeared surprisingly, almost shockingly dark. Not the luminous, pale golden world that Cassini had photographed and that Hubble had captured in its iconic visible light portraits. In the wavelengths JWST was designed to observe, Saturn's disk was deeply, almost eerily subdued, absorbing mid-infrared radiation rather than reflecting it, in a way that initially puzzled the team. Let that image rest with you for a moment, if you can. The planet we associate more than any other with visual splendor, the great ring jewel of the outer solar system, appearing to JWST's extraordinarily sensitive eyes as something dark and enigmatic. There is something philosophically interesting in that reversal. Something that speaks to the way knowledge transforms perception. What looks beautiful and bright in one kind of light can appear strange and quiet in another. The universe does not have a single face. It has as many faces as there are wavelengths of light to see it in. What caused this darkness, this unexpected absorption, was methane. Saturn's atmosphere contains significant quantities of methane gas, and methane is a powerful absorber of mid-infrared radiation at specific wavelengths, the very wavelengths that JWST was observing. The planet was, in a sense, swallowing its own light, the methane in its upper atmosphere acting like a deep dimmer, muffling the thermal glow from the warmer layers below. This was not entirely unexpected from a theoretical standpoint. Scientists had known that methane absorption would affect JWST's view of Saturn. But the depth and extent of the absorption, and the extraordinarily fine detail with which JWST resolved the atmospheric structure responsible for it, exceeded expectations. Researchers could see, in the infrared data, the vertical structure of Saturn's atmosphere in a way that had never before been possible from Earth orbit, the layering of cloud decks, the subtle temperature gradients between different atmospheric strata, the faint glow of the polar regions where methane absorption was slightly less intense and the deeper atmosphere could breathe through. But the atmosphere, remarkable as it was to examine in this new light, was not where the most scientifically consequential discoveries waited. It was the rings that held the secret. And as the team worked through the spectroscopic data, those beautiful cascading graphs of light intensity plotted against wavelength, each peak and trough a chemical signature waiting to be identified, what they found began to shift the conversation in ways that will take years to fully absorb. The spectroscopic data from JWST's NIRCam and MIRI instruments revealed the ring system in chemical detail that simply had not been accessible before. The broad sweep of the A and B and C rings, the dark gap of the Cassini division, the tenuous inner rings closer to the planet, all of these showed distinct and measurable spectral signatures. And the team found something that, when they understood its implications, began to reshape the debate that had been running through the scientific community for decades. What JWST detected was a pattern of thermal emission and chemical absorption that was consistent, in several key respects, with a ring system of relatively recent origin. The spectral fingerprints of the ring ice showed a composition and crystalline structure suggesting that the material had not been subjected to the billions of years of radiation bombardment and micrometeorite contamination that an ancient ring system would have accumulated. The thermal signatures suggested ring particles that were, in the relevant chemical sense, relatively fresh, not pristine, not untouched by the environment of space, but far less processed and altered than what scientists would expect to find in a 4-billion-year-old ring system. The data also offered new insights into the distribution of non-ice contaminants across the ring system, the silicate dust and organic compounds that gradually accumulate over time from micrometeorite impacts. JWST's infrared sensitivity allowed researchers to map these contaminants with unprecedented spatial resolution, tracking their concentration not just across the broad zones of the ring system but within individual ring regions, examining how the contamination varied between the inner and outer rings and what those variations might imply about the history of the ring material. What they found was a pattern of contamination that was, in important ways, consistent with a young ring system, one that had begun relatively pure and had been gradually accumulating dirt and silicate material over a period of hundreds of millions of years rather than billions. The innermost rings, which would logically have been receiving the highest rate of contamination from Saturn's own atmospheric particles raining outward, showed higher contamination levels than the outer rings, in proportions that aligned better with a young ring scenario than an ancient one. Now, it is important to be precise here, because this is the kind of finding where imprecision leads to misunderstanding. JWST did not definitively prove that Saturn's rings are young. Science rarely works by absolute proof, it works by accumulating evidence, by finding that one hypothesis better explains the totality of observations than competing hypotheses, by steadily narrowing the range of plausible explanations until the most likely story becomes clear. What JWST did was add a new and uniquely powerful set of data points to a debate that had been ongoing for decades, and those data points tilted the weight of evidence more clearly than ever before toward the young rings hypothesis. The chemical fingerprints of the ring ice, the thermal emission patterns, the contamination distribution, the spectral signatures of both organic and silicate contaminants, all of these, interpreted together, painted a portrait of a ring system that was not 4 billion years old but considerably younger. The precise age estimate derived from JWST's data placed the rings in a range that overlapped significantly with the Cassini estimates, somewhere between roughly 100 million and 400 million years old, with the mid-range estimates clustering around 200 to 300 million years. To put that in context, 200 million years ago on Earth, the age of early dinosaurs was just beginning. The supercontinent Pangaea was still slowly breaking apart. The Atlantic Ocean was a narrow sea, barely wider than the Mediterranean is today. If Saturn's rings formed at around that time, born from the catastrophic destruction of some now-vanished moon, or the capture and tidal disruption of some wandering icy body, then the solar system that gave rise to them was already ancient, already billions of years old, already home to planets and moons and asteroid belts and comets that had been orbiting in their established paths for eons. And in the midst of all that ancient, settled architecture, something new was happening around Saturn. Something violent and beautiful was being born. And here is where the story becomes almost dreamlike in its implications, because the question of what created the rings, what event, what catastrophe, what chance encounter, is itself a mystery that the JWST data helps illuminate, though it cannot yet fully resolve. The most favored hypothesis among planetary scientists today, and the one that the JWST data appears most consistent with, involves the disruption of a moon. Not one of Saturn's current moons, which continue to orbit peacefully in their established paths, shepherding the ring edges and carving the gaps, but a hypothetical ancient moon, now gone, that once occupied an orbit close to Saturn and was, perhaps through gravitational interaction with another body, gradually pulled inside Saturn's Roche limit, that critical distance from a planet inside which tidal forces overwhelm the self-gravity of any bound object, tearing it apart the way a wave tears apart a sandcastle at the water's edge. When a moon crosses the Roche limit, it does not simply disintegrate all at once. It stretches, it deforms, pieces begin to break away, the self-gravitating coherence that holds a world together begins to lose the battle against the tidal forces trying to pull it apart. The final breakup might unfold over millions of years, a slow-motion unraveling in cosmic time, each fragment eventually spreading into the orbit-following sheets and streams that we recognize as a ring system. And because moons, especially those that form in the outer solar system, are composed largely of water ice with varying amounts of silicate rock mixed in, such a disruption could plausibly produce a ring system of the composition and extent we observe around Saturn today. There is a version of this story that has been given a name in the literature, the chrysalis hypothesis, proposed by a team of researchers in 2022, which suggested that a lost moon they called Chrysalis may have interacted gravitationally with Saturn in a way that not only led to the moon's eventual disruption and the formation of the rings, but also accounts for Saturn's unusual axial tilt. Saturn is tilted about 27 degrees relative to the plane of its orbit, a tilt that has long puzzled planetary scientists because it does not fit neatly into standard models of how the planets formed and settled into their current configurations. The chrysalis hypothesis suggests that the gravitational resonance between this lost moon and Saturn's orbital relationship with Neptune could explain that tilt, making the hypothetical moon responsible for two of Saturn's most distinctive characteristics simultaneously. The JWST data, while it cannot directly confirm the existence of chrysalis, is consistent with the timeline this hypothesis requires. A disruption event occurring somewhere between 100 and 400 million years ago would fall within the range suggested by both the Cassini mass measurements and the JWST spectroscopic data. The chemical signatures of the ring ice, relatively fresh, not extensively processed, showing patterns of contamination and composition that fit a young ring scenario better than an ancient one, all of this aligns, piece by piece, with a picture in which Saturn's most iconic feature is a relatively recent addition to the planet's appearance. Let yourself drift with that thought for a moment. The rings of Saturn, which seem to us so permanent, so eternal, so utterly definitive of what Saturn is, those rings may not have existed when the first multicellular animals were diversifying in Earth's ancient seas. They may have formed sometime around the same geological era as the first forests, the first insects, the first amphibians crawling up onto the shores of ancient continents. The solar system was old. The planets were old. And then, on one particular world in one particular orbit, something broke apart and spread itself into a halo of ice and light that would one day, billions of years later, become the most recognized shape in all of astronomy. There is something humbling in that. Something that invites a particular quality of wonder, not the dazzled wonder of first encounter, but the deeper, quieter wonder that comes from understanding. From knowing not just that something is beautiful, but why it is beautiful, and how long it has been beautiful, and how long it will remain so. Because the rings are temporary. We know that now. We have known it since Cassini measured the rate of ring rain and gave us the rough arithmetic of their remaining lifespan. Within perhaps 100 million years, a heartbeat in cosmic time, the rings will be gone. The ice particles will have spiraled gradually inward, drawn by Saturn's gravity and depleted by erosion, until what is left is too thin to see, too thin to cast those extraordinary shadows across the planet's face, too thin to be the first thing anyone describes when they try to explain what Saturn looks like. Future civilizations, if they arise elsewhere in the cosmos and turn their telescopes toward our solar system in 100 million years, will see a different Saturn. A Saturn stripped of its halo, bare and unadorned, just another gas giant orbiting in the cold outer reaches of a nondescript yellow star. They will have no way of knowing what it once wore. They will have no record, unless we somehow leave one, of the rings that graced it for a brief and magnificent interval in the middle of its long history. We are here at exactly the right moment. Not just to see the rings, but to understand them. JWST has given us the tools to look at Saturn and read its rings as a story, not a story written in ancient stone, as we once assumed, but a story written in the relatively recent past, in ice and light and the slow mathematics of orbital mechanics. A story still unfolding, even now, as you lie in the quiet and let your eyes grow heavy and the shapes of rings and moons and distant atmospheres blur gently at the edges of your consciousness. The spectroscopic data from JWST continues to be analyzed. There are details in those cascading wavelength graphs that planetary scientists are still working through, still debating, still drawing new conclusions from. Science is not a single moment of revelation, it is an ongoing conversation, a slow and careful and endlessly self-correcting process of listening to what the universe is trying to tell us and refining our understanding one careful measurement at a time. But the weight of evidence has shifted. The conversation has changed. The ancient rings hypothesis, which once seemed entirely plausible and had many distinguished defenders, now has a much harder case to make. Not impossible, science should never say impossible when what it means is unlikely, but significantly harder. The young rings hypothesis, supported by Cassini's mass measurements, by ring rain erosion rates, and now by JWST's unprecedented chemical fingerprinting of the ring material itself, has moved from being one side of a balanced debate to being the position that the majority of planetary scientists find most consistent with the full body of evidence. And somewhere in that shift, in the quiet and gradual accumulation of evidence that finally tipped a decades-old debate toward resolution, there is a lesson worth carrying with you into sleep. Sometimes the most profound discoveries are not sudden. They are not lightning strikes or eureka moments, though those make for better stories. Sometimes they are the slow, patient, incremental work of accumulating understanding, one spacecraft, one telescope, one measurement at a time, until what was hidden is hidden no longer, and a mystery that has occupied some of the finest scientific minds for a generation finally, gently, yields its answer. Saturn's rings, it seems, are young. Younger than the dinosaurs. Younger than the first flowers. Born in a cosmic event we were not here to witness and cannot yet fully reconstruct, but whose signature is written in the light that JWST so carefully gathers, in the chemical fingerprints of ice particles drifting in the cold silence 200 million kilometers and more from where you are resting now. Let that distance settle around you like the dark. 200 million kilometers. You cannot hold it as a number, no mind can truly hold such distances. But you can feel it as a quality, a vastness, a silence so deep it becomes almost tangible, almost warm, in the way that all truly great silences eventually do. The rings are out there now, as you rest. They are catching the distant light of the sun, that pale, cold light that reaches Saturn reduced to perhaps 1% of its intensity at Earth, and scattering it, reflecting it, spinning it in slow wheels of ice and shadow. The Cassini division is dark against the brightness of the B ring. The faint C ring lies inward, barely luminous, already thin, already old in its own way even if it is young by the standards of the solar system. The shepherd moons patrol their invisible boundaries, herding the ice particles back into line with the gentle insistence of gravity. And somewhere, on a telescope floating 1.5 million kilometers from Earth in the cold beyond our moon's orbit, JWST continues to observe. To measure. To add its voice to the long conversation between human curiosity and the deep, patient, endlessly generous universe that surrounds us. This is what we are when we are at our best. Curious. Patient. Willing to look again and again at the same object from new angles, with new instruments, with new questions, until the thing that seemed obvious reveals its surprise and the thing that seemed settled reveals its depth. You can let your breathing slow now. Let the details of rings and spectra and contamination rates and ring rain and lost moons dissolve gently into the background, the way details always do when you are drifting toward sleep. What remains is not the data but the feeling of having looked at something immense and beautiful and begun, however imperfectly, to understand it. Saturn is out there. The rings are real. JWST is watching. And you are here, in this quiet moment, at the edge of sleep, which is itself a kind of voyage, inward and deep and full of its own quiet wonders. Let the rings carry you. Let the soft cold light of distant ice be the last thing your mind holds before it releases even that, and you drift, as ring particles drift, in slow and patient arcs through the warm dark of sleep. And so we arrive, gently, at the place where all great journeys eventually lead, not to an ending, exactly, but to a kind of settling, the way a ring particle, after traveling vast distances across the face of a giant planet, finally finds its place within the slow and patient architecture of the rings themselves, and simply rests there, turning. There is something worth pausing on, something worth holding for just a moment before we let the science dissolve into the softer language of wonder and sleep. And that is this: Saturn has been visible to human eyes for as long as human eyes have looked upward. Ancient Babylonian astronomers tracked its slow path across the sky. Greek philosophers gave it a name and a meaning. Medieval scholars wove it into their understanding of time itself, associating this slow-moving golden wanderer with the God of ages, with patience, with the long turning of things. And through all of that time, through thousands of years of careful watching, Through centuries of telescopes pointed at that soft golden light, Saturn kept its deepest secret entirely to itself. The rings were there, of course. Galileo saw something strange about Saturn in 1610, though his telescope was too crude to resolve what it was. He thought perhaps Saturn was a triple planet, a large body flanked by two companions. When he looked again 2 years later and the companions seemed to have vanished, he was baffled, even disturbed. He wrote that Saturn had devoured its own children, invoking myth to explain what his instruments could not. It was Christian Huygens, 50 years later, who first understood that what surrounded Saturn was a ring, a flat, continuous disk of material circling the planet in its equatorial plane. And from that moment of recognition forward, the rings became perhaps the most iconic structure in all of astronomy. Every child who has ever looked through a telescope and seen them has felt that same shock of beauty, that same sense that the universe has revealed something almost impossibly elegant. But here is what all those centuries of watching could not tell us. Here is the secret that persisted through Galileo and Huygens and Cassini the astronomer, not the spacecraft, but Giovanni Cassini, who in 1675 discovered the great gap in the rings that now bears his name, and through William Herschel and through the Voyager flybys and through decades of dedicated Earth-based observation. The secret was simply this: how old are they? When did they form? Are these rings a feature of Saturn that has existed since the planet itself was born, 4.5 billion years ago, a primordial structure as ancient as the solar system itself? Or are they something newer, something that arrived relatively recently in planetary terms, the shattered remains of a moon or the captured debris of a comet, assembled into their current breathtaking form perhaps only a few 100 million years ago, when dinosaurs still walked the surface of our world? That question, the deceptively simple question, turned out to be one of the most stubbornly resistant puzzles in all of planetary science. And it took a telescope the size of a tennis court, positioned 1 million miles from Earth at a gravitational balance point called L2, operating in the cold infrared silence of deep space, to finally begin to answer it in a way that most scientists find genuinely convincing. Think about what that means for just a moment, as your body grows heavier and your breathing grows slower. It means that something visible to the naked eye, something that has inspired human wonder for millennia, something that has been studied with increasingly sophisticated instruments for 400 years, held a fundamental mystery about its own nature that we simply could not solve until now. It means that the universe's capacity to surprise us does not diminish as our tools improve. It means that every answer we find is nested inside a larger question, and that larger question inside a still larger one, in an infinite regression of mystery that extends in all directions, outward toward the cosmological and inward toward the quantum, and that we, in our brief and luminous moment of consciousness, get to stand at the intersection of all of that and simply wonder. JWST did not solve everything. Let us be honest about that, as scientists always try to be, even when they are excited, even when the data is beautiful and the findings are genuinely thrilling. There are still questions about Saturn's rings that remain open. The precise mechanism of their formation, whether it was a single catastrophic collision, a slow gravitational disruption, a captured visitor from the outer solar system, has not been definitively established. The exact timing, measured in millions rather than billions of years, is still a range rather than a single number. The long-term fate of the rings, which we know are slowly raining inward onto Saturn's atmosphere and will eventually disappear on a timescale of perhaps 100 million years, is understood in broad strokes but not in fine detail. Science is always like this: each answered question illuminates the shape of the next unanswered one, and the territory of the unknown, rather than shrinking, seems somehow to grow more interesting with every expedition. But what JWST gave us was something enormously valuable. It gave us a new kind of certainty about composition, about thermal behavior, about the spectroscopic fingerprints of ring material in wavelengths of light that had never been examined with this level of precision from this distance. It confirmed, with a weight of evidence that shifted the center of scientific opinion, that Saturn's rings are young, cosmically young, geologically young, young in a way that places their formation well within the era of complex life on Earth. And it opened a doorway into understanding ring systems not just as beautiful accidents but as dynamic, evolving structures that planets can acquire and lose over the course of their long lifetimes. This changes how we think about the solar system in ways that are still unfolding. If Saturn's rings are young, then what we see when we look at Saturn today is not what Saturn looked like a billion years ago, and not what it will look like a billion years hence. Saturn has had, perhaps, other rings before these, formed from other moons, other collisions, other events whose traces have long since been swept away. And planets throughout the galaxy, planets we cannot yet resolve into anything more than a point of light shifting slightly against the background of stars, may have their own rings forming and dissolving in the darkness, invisible to us, cycling through their brief and gorgeous existence with no one watching. But someone is watching Saturn. JWST is watching. And the community of scientists who devote their working lives to understanding this planet and its extraordinary system of moons and rings and magnetic fields and weather, that community is larger and more energized than it has been in years, because JWST has reminded them that there is still so much to discover, still so much that the data will reveal if you ask it the right questions with the right instruments at the right moment. There are missions being proposed and planned. The Cassini mission ended in 2017 when it was deliberately guided into Saturn's atmosphere, its fuel exhausted, its mission complete, its final transmission received and processed by engineers who had spent decades of their professional lives working with this extraordinary spacecraft. And since then, Saturn has been observed from a distance, from Hubble, from ground-based telescopes, and now from JWST. But there are scientists who dream of returning, of sending another dedicated spacecraft to orbit Saturn and study it from close range, to dive repeatedly through the rings the way Cassini did in its final months, to land on Titan with its methane lakes and nitrogen atmosphere and prebiotic chemistry, to send a probe beneath the ice of Enceladus where a liquid water ocean hides in the dark and hydrothermal vents may be producing the conditions that led to life on Earth. These missions are not yet funded, not yet built, not yet launched. They exist for now in the patient language of proposals and white papers and scientific conferences where researchers make the case for why Saturn deserves another dedicated emissary from our small and curious planet. But the history of planetary science suggests that they will come, eventually, because human curiosity has a way of finding its path toward the things that fascinate it most, and Saturn has always fascinated us. In the meantime, JWST continues its work. The telescope has observation programs dedicated to Saturn that will run for years, accumulating data, refining measurements, watching for changes in the ring system and the atmosphere across time. Each new dataset adds another layer of understanding, another constraint on the models, another piece of the puzzle that will one day, perhaps, give us the complete story of how this extraordinary structure came to be. And there is something profoundly comforting about that, if you let yourself feel it. The work continues. The questions remain. The telescope turns in its slow orbit around the second Lagrange point, 1,000,000 miles from home, its golden mirror cooling in the shadow of its sunshield, gathering light that has traveled across the solar system and beyond, and turning it into knowledge. Night after night, observation after observation, the universe speaks in the language of photons and spectral lines and thermal signatures, and we listen, and we learn, and gradually, patiently, we understand a little more than we did before. You have traveled a long way tonight. You have moved from the first strange observations of a distant golden planet to the cutting edge of infrared astronomy. You have sat with the scientists who argued about ring ages for decades, who built instruments and designed missions and pored over data looking for the answer to a question that seemed almost too simple to be so difficult. You have followed the Cassini spacecraft through its grand finale, that beautiful and bittersweet final plunge into the atmosphere of the planet it had spent 13 years studying. You have looked through the eyes of JWST at the dark infrared image of Saturn, that strange and surprising reversal where brightness becomes darkness, where the familiar becomes alien, where science reveals something beneath the surface of appearances that changes how you understand what you are seeing. And now you are here. In this quiet place. At the edge of sleep. Let your body be heavy. Let it sink into whatever surface supports it, the bed, the pillow, the slow and patient pull of gravity that keeps you here, that keeps all of us here, the same force that holds Saturn's rings in their orbits, that keeps the moons in their slow elliptical dances around the planet, that governs the motion of everything from the smallest ice crystal in the B-ring to the largest galaxy cluster in the observable universe. Gravity is patient. It does not hurry. It simply holds, and in its holding, creates the conditions for everything. Let your breathing slow now, if it hasn't already. In, slowly, and out, the way the atmosphere of Saturn moves in its great banded currents, the way winds circle the planet in belts of amber and gold, the way storms larger than the entire Earth form and dissipate across those vast amber skies. You are breathing with the universe tonight. Your breath is part of the same story, the same atoms, the same chemistry, the same improbable chain of events that began with the Big Bang and led, through the formation of stars and the explosion of supernovae and the slow cooling of protoplanetary disks, to a planet with rings and a moon with methane lakes and a small blue world with conscious creatures who built a golden telescope and pointed it at a mystery. Saturn is still there, you know. Even now, in this moment, as your awareness begins to soften at its edges and the details of the day recede. Saturn is there, moving in its slow orbit, carrying its rings through space, its 60-plus moons tracing their complex gravitational ballet around it. Titan is turning, its thick orange haze lit faintly by a sun that is 10 times smaller than the one that warms our mornings. Enceladus is venting its plumes of water vapor into the vacuum, a tiny world with a secret ocean and a breath of ice crystals trailing behind it like a whisper. The rings are turning, each particle in its own orbit, a vast slow clockwork of ice and rock and ancient light. And JWST is watching, quietly, patiently, gathering light in the infrared, building a picture of a world that still has secrets, that will always have secrets, because that is the nature of the universe, generous with its revelations and inexhaustible in its mysteries, always offering something more to anyone willing to look closely enough. You have looked closely tonight. And what you found, at the center of all the science and all the history and all the data, is what you always find when you look at the cosmos with real attention, a feeling of belonging to something vast and beautiful and ongoing. A feeling that your brief and luminous consciousness is not separate from all of this but woven into it, made of it, continuous with it in ways that physics and chemistry confirm even as they remain somehow beyond the reach of words. You are made of stardust. This is not a metaphor. The carbon in your body was forged in the cores of stars that burned and died before our sun was born. The iron in your blood was scattered across space in the violence of stellar explosions. The water in your cells was assembled in molecular clouds and delivered to the young Earth by comets and asteroids. You are, in the most literal sense, a product of the same processes that formed Saturn and its rings and the ice crystals that catch the light of a distant sun and scatter it into the golden shimmer that has transfixed every human eye that has ever turned a telescope toward that part of the sky. So when you look at Saturn, you are not looking at something alien. You are looking at something that shares your origin, something built from the same raw materials by the same forces, something that has simply traveled a different path through the 4.5 billion years that separate the formation of the solar system from this quiet moment, this soft night, this gentle approach to sleep. Let that thought carry you now, not as an idea to analyze or a fact to remember, but as a feeling, a deep and restful feeling of connection, of belonging, of being part of something so large and so old and so beautiful that your small human worries and the details of your daily life simply cannot compete with it. They recede. They grow small. They become the tiny things they always were against the backdrop of a universe 14 billion years old and 90 billion light-years wide and still, astonishingly, producing places of such improbable beauty as a planet wrapped in rings of ice, glowing in the dark like a jewel, keeping its secrets for billions of years and then, at last, whispering them to a golden mirror drifting in the cold silence beyond the moon. Your eyes are closed, or they are closing. The images from tonight's journey, the false color infrared of Saturn's darkened disk, the spectroscopic graphs with their peaks and valleys, the Cassini photographs of ring shadows stretching across the planet's face, the golden hexagonal storm at Saturn's north pole, the pale blue crescent of Enceladus against the black, these images are softening now, the way all images soften when the mind turns toward sleep. They are becoming impressions rather than pictures, feelings rather than facts, the gentle residue of wonder rather than the sharp edges of information. This is how knowledge settles into us, really. Not through effort but through release. The facts you have encountered tonight will arrange themselves, without your conscious attention, into understanding. Your sleeping mind will do the work that your waking mind was too busy to complete. Tomorrow you will know Saturn a little differently than you knew it yesterday, and you may not be able to say exactly what changed, only that something shifted slightly, the way a ring particle shifts in its orbit when it passes close to a moon, diverted by an invisible force into a new path that carries it somewhere it has never been before. Let the rings carry you. Let the soft cold light of Saturn be the last image your waking mind holds, that golden warmth, those graceful arcs of ice catching light across a distance of nearly 900 million miles, the shadow of the rings falling across the face of the planet in long curved lines like the marks that time leaves on everything it touches. You are drifting now. And drifting is exactly the right word. Not falling, not rushing, not going anywhere in particular, but moving in that easy unhurried way that rings move, that moons move, that planets move in their great patient orbits, carried by gravity, which is just another word for the universe holding you close, held, and warm, and turning slowly in the dark. Breathe out, and let the universe be as large as it is. Let Saturn be as far away as it is. Let the questions about rings and ages and origins and futures be as open as they are. None of it requires your attention now. The scientists are sleeping too, or they are working, or they are doing whatever people do when they are not at their telescopes, and tomorrow the data will still be there, the questions will still be there, JWST will still be there, gathering light in the patient and unhurried way that is the only way the universe knows how to do anything. And you will still be here, rested, warm, held by the same gravity that holds the rings, breathing the same air that connects you to every living thing that has ever looked up at a night sky and felt small and vast at the same moment, felt the paradox of being an infinitesimal point of awareness in an incomprehensible cosmos and somehow, impossibly, being large enough to comprehend it. Sleep now. Let the rings turn without you for a while. They will be there when you wake. Saturn will be there. The mystery that JWST began to solve and the new mysteries that its solution opened, all of that will be there, patient and glowing and full of questions, waiting for the next curious mind to turn toward it and ask. But for now is for rest, for the quiet dark, for the slow and gentle voyage inward that every sleeping mind takes each night, down through the layers of consciousness into something deep and still and profoundly, completely, at peace. The rings are turning. Saturn is glowing. JWST is watching. And you are already somewhere else, somewhere quiet and deep and warm, where the universe holds you as it holds everything, with patience, and with gravity, and with a care so vast it has no name. Good night.